Okay, good day. It's AP Calculus. I am Mr. McCulley. This is the presentation on section 2.6 related rates, and we need to get right into it. So today we're going to talk about implicit differentiation and how it works with related rates. We are going to find related rates, and then we are going to solve some related rate problems. In fact, this is what we're going to mostly do. So just real quick here, related rate problems are nothing more than an application of implicit differentiation. So last section we looked at how to do implicit differentiation, and in this particular section we are going to do applications for it. So my first example is this thing, and I want to kind of break it down, and I have some notes for the breakdown of it, and then we're actually going to do it. The volume of a cube is expanding at a rate of 15 centimeters cubed per minute. At what rate is the length of a side expanding when the side is 10 centimeters long? So first, here we have a rate. It is a volume in terms of time. So when we look at this thing right here, okay, we are thinking the change in volume over time. That is a derivative. At what rate is the length of a side? So there's my question. I'm trying to find the rate at which a side is expanding when my side S is 10 centimeters long. So how implicit differentiation applies here? We know that the rate that the volume is changing, or you know the rate at which the volume is changing. So the volume is changing at a constant rate of 15 centimeters cubed per minute. So someone's opened a valve and they've just left it go. All right. And it's blowing up a cube-shaped balloon. I don't know why it's a cube-shaped balloon, but there you go. And so they want to know how fast the side is expanding when a side is exactly 10 centimeters long. Okay, so these two rates, the rate of which the volume is changing and the rate at which a side is changing, are related because of the equation for volume of a cube. Both rates are derivatives with respect to time, but the volume equation is just a function of the length of a side. So think of it this way. When the cube is small, if you're pouring a certain volume into it, it's going to expand very fast right away. But when the cube gets bigger, because volume is a cubic expression, if I'm still pouring that in at a constant rate, it's not going to make this expand nearly as fast. So when I look at this thing, the volume of a cube is expanding at a rate of 15 centimeters cubed per minute. That, in my mind, is dV over dt equaling to 15 centimeters cubed per minute. At what rate is the length of a side expanding? Here is my side, and they are asking, how is S changing with respect to time? That's what I'm looking for when S is exactly 10 centimeters. All right, so I have this volume equation. There are no rates here, but if I derive this equation with respect to time using implicit differentiation, what we learned yesterday, notice that dv or t and v are not the same variable. So we want to consider v is some function of t. And when I do that derivative, I get dv over dt. Again, doing the derivative of s to the third with respect to t, s is not t. So S represents some function of t. And so when we do that, we've got a composition of functions, the t to the third function and the s function. It's going to be using the general power rule. It's going to be s to the, do it right, 3s squared. And now the placeholder for s is ds over dt, the derivative of s. So we've done a implicit differentiation and we've used the chain rule on s. Now when I look at this thing, I've got 1, 2, 3 variables. I got 1, 2, 3 variables. I have one unknown. If I plug in the 15 for dv over dt, I have 3, s equals 10. and then ds over dt. Well, hey, need my squared, and I look at this and I say, oh, I only got one variable left, and it's the one I'm looking for. So I can say that ds over dt is equal to 15 over 300, and then 15 over 30 is a half with a 0 left over, so 1/20th, and this is going to be centimeters per minute. Now here's the thing. Notice, if the length of a side is bigger, this expression becomes bigger, so ds over dt is going to slow down. So the bigger the cube is, if the volume is changing at a constant rate, the bigger that the cube is, the slower that the length side is going to grow, which is kind of what we talked about at the beginning. So just some guidelines to do related rate problems, and I'm taking this directly from page 150 in your book. First thing you want to do is identify all the given quantities and quantities that need to be determined. You may have to use the original equation to determine an unknown, and we're going to do that in the next problem. Second, you need to write an equation that involves all of the variables whose rates of change are either given or need to be determined. Okay? In this one, we had a rate of change that was given, and we had a rate of change that needed to be determined. And then we're going to use the chain rule to implicitly differentiate both sides of the equation with respect to the common rate variable. In most cases, it's time, but it's not always the case. And then after completing step number 3, we're going to substitute into the resulting equation all known variables for the variables and their rates of change, and then solve for what we were looking for, what needed to be determined. All right, so my second example. One plane leaves an airport at 12 p.m. flying due north at 300 miles per hour. A second plane leaves the airport flying the same due west at a rate of 400 miles per hour. After 3 hours, at what rate is the distance between the planes changing? Now, if you've had physics, and I know some of you have, you know that vectors can be used as linear quantities. So if I were in physics and I was doing this, I would just use the chain rule, or excuse me, the Pythagorean theorem on these two vectors and call this one. All right, that's how I would do it, because the rates at which they're flying doesn't change, and so the vector quantities won't change. Okay, that's the physics way. That being said, I do want to do it as if it were a related rate problem, just to show that it will work. So when I'm thinking about this, I have this one here, or this northerly distance is 300 miles per hour. That is a change in A over time, if I call this side A. This one here is 400 miles per hour, and that is going to be a change in B over time if I call this B. And they want us to find dc over dt. That's what we want to find if I call this C. So just real quickly, making a list of everything that's known, unknown, and needs to be determined, I could say that dA over dt is 300, dB over dt is 400, dC over dt, that's what I am looking for. When I get this value, I know I'm done. But I also have the variables A, B, and C. So let's talk about a way to relate the sides. Well, Pythagorean theorem, a squared plus b squared equals to c squared. And this is one of the reasons why the vector solution will work, because when I do all these derivatives with respect to time, I will get a proportionality, which is a linear relation, which will allow me to do that. But I am deriving with respect to time. So I go through and I do since all of these variables are different than the value which we are deriving with respect to, This thing is going to be 2a times dA over dt. This one will be 2b times dB over dt. And this one will be 2c times dC over dt. Now here's the thing. I've got 1, 2, 3, 4, 5, 6 variables. I've got only 2 known quantities. Well, I'm looking for this one, so that reduces it by 1. But I still need A, B, and C. Well, I could divide everything by 2 and cancel out the 2's if I wanted to, and I'll do that in the next step. But I can figure out what C is too after that time, because after 3 hours, A is going to be 900 miles. After 3 hours, B is going to be 1,200 miles. All right. And since I have distances, I could use the Pythagorean theorem. And again, I don't have my smart view, so you're going to have to trust me when I start hitting these calculator keys that I'm doing it right. So if I say the square root of 900 squared plus 1,200 squared, that is a 1,500. Now, I've calculated all of these things, so I've got 900 miles, I've got 1,200 miles, and I've got 1,500 miles. So I can plug in all of these values. I can say 2 times 900. Actually, didn't I say I was going to cancel out that 2? I did. So I'm going to cancel everything was divided by 2. So I've got 900 times dA over dt plus 12, and not very good. Let's do a better job. Plus 1,200 times, let's see here. I know what dA over, I know what all these are. Darn it. All right, so we're plugging in now. So I've got 900 times 300, because I know that dA over dt is 300, plus 1,200 times dB over dt, which I know to be 400. And then C, I know to be 1,500, and that's going to be my dC over dt, which I don't know and I need to determine. So, and I need an equal sign here, not a plus. That's equals. Just bring that down. Okay. So, calculation time. I need to do this plus this divided by 1,500, and that'll give me dC over dt. And so 900 times 300 plus, let's see here, 1,200 times 400 equals 750,000. That's what it is. And then I divide that by 1,500, and we do get 500 miles per hour. And again, we already knew that, but we showed that the application does hold true. And we needed to do that because this next one is a skosh more challenging. So I didn't write down the whole problem. I am going to read it. It is from page 155 in the book, and it is number 24. So it says a trough is 12 feet long and 3 feet across the top. See the figure. Its ends are isosceles triangles with an altitude of 3 feet. If water is being pumped into the trough at 3 cubic feet per minute, how fast is the water level rising when the depth h is 1 foot? Okay. So let's mark this up here. This is 12 feet, it's not changing. This is 3 feet, it's not changing. This is 3 feet, it's not changing. This distance here is also 3 feet. Let's make them all feet, and they are not changing. Here's the thing. When I'm dumping water into here, this is going to be rising. And so this distance D is changing, and this distance here, H is changing. Now, here's the good news. Since this is always constant, we can call that's never going to change. Regardless of how high this water is, from here to here is always going to be 12 feet. That's good. That removes one variable. And while I'm talking about variables, let's talk about how do I calculate the area or the volume of the water? Well, the volume of any right prism is the area of the base times the height. And in this case, the volume is going to be H times 1/2 B and then h, and I'm going to change this as that doesn't make a whole lot of sense because it's not the same h. We'll just call this length, and that length here is going to be 12. All right, so that'll help. All right, now this is an isosceles triangle. So just real quick, the front of this trough here is going to look like this, where these two sides are the same length. And so this base here and this height here is going to be proportional to this 3-foot distance here and this 3-foot height here. So I can literally say that 3 is to 3 as b is to h. And so cross multiplying, I can say that 3h is equal to 3b, and then h is equal to b. So I can come over here and start filling in the blanks of what I know. V is equal to 12, that's my length here, times 1/2 times, and we want to know at what rate the height is changing. So since b and h are equal, I can say this is h squared, and then say this is 6h squared. And so that is my volume of the water, which is good. All right, so let's start writing some stuff down. I know that dV over dt, the change in the volume, is, let's see here, 2 cubic feet per minute. So 2 foot cubed per minute. They want to know at what rate the height is changing, dH over dt, when h is specifically 1 foot high. All right, well, if I take this equation, v equals to 6h squared, and I derive that with respect to time, that's a d, I'll get dv over dt is equal to 2 times 6 is 12, h, and then I need the, since I'm deriving implicitly, I need the placeholder for the derivative of whatever h is, dh over dt. Notice that's what we're looking for. All the variables that we have been determined. So I can say that this is 2, I can say this is 12 times 1 times dh over dt. And so then I can say that this is 1/6 is my dH over dt, which is 1/6 foot per minute. And that was part A. Part B says if the water is rising at a rate of 3/8 of an inch per minute when h equals 2 feet, determine the rate at which the water is being pumped into the trough. So in this particular instance, they say the change in h over t is, what did I say it was? 3/8 inch per minute. And then they say that when the height is 2 foot, what is the change in volume? dV over t, that's what we're looking for. Now, we need to make this change here. So there are 12, let me see here, there are, in 1 foot, there are 12 inches. So I can multiply the bottom by 12, and that'll give me a 3 cancels in the 12 and cancels there. That'll leave me with 4. 4 times 8 is 32. So I have 1 over 32 feet per minute. And I had to make that change because I had a sign, a change in units from inches to feet. But I don't have to, I've already got the equation that, I've already done that derivative. Let's use that, okay? dV over dt is equal to 12h times dH over dt. In this case, I know what h is, I got it right there. I know what dH over dt is, I have it right there. I can just plug and chug. I got 1 over 32, And so the change in volume for this one, after I've multiplied all this, got 24 over 32. That reduces down to 3/4, and this is going to be foot cubed per minute. Okay, last one. And this one says that we are going to, number 44, I'm just going to read it. It says, an airplane flies an altitude of 5 miles towards a point directly over an observer. See the figure. The speed of the plane is 600 miles per hour. Find the rate at which the angle of elevation theta is changing when the angle is 30 degrees. That's part A. There's two other parts. But since this is running long, this is going to be the only part that I do. So the question says that they know the height, and we'll call it h here. The height is 5 miles. Now, and they also say that theta is 30 degrees. They also say that this, we'll call it g here, this ground rate is changing. This ground rate is changing at a rate of negative 600 miles per hour. Now we know it's negative 600 because it's going towards the observer. If the observer's here and the little airplane, there's the wings, are flying towards us, it's a negative 600 miles per hour. All right, so we do know that. And they want us to figure out d theta over dt. All right, so first off, just because it is calculus, let's change this to radians. So asking you to remember back to last year, 30 degrees is pi over 6 radians. And that's always good to know. And this is what we're trying to figure out. So let's see here. I know that h is 5, so let's put a 5 right there. And let's put a 30, actually let's use pi over 6 since we're doing it. Let's use pi over 6. Now, let's see, what is a equation that relates an angle measure here in a right triangle with this side, which would be the opposite side, and this side, which would be the adjacent side? That, to me, looks like the tangent of theta is equal to, in this case, h over g, I guess, opposite over adjacent. And even though I don't know what g is, let's do this and see if I need that, because I do know that dg over dt is negative 600 miles per hour. Maybe I won't need to. So since I'm trying to find d theta over dt, what we do want to do here is we want to derive with respect to time. So the derivative of tangent is secant squared, and then I'll have my theta. But since this is the composition of functions with respect to time, I have to put in that placeholder d theta over dt. Now, this is what I'm looking for, and so that is always good news. Now, unfortunately, on this side, though, I have to do a quotient rule. So we have to remember ho d high minus high d ho all over ho ho. So ho d high, g times dh over dt minus high h times d ho, which would be dg over dt all over ho ho, which is g squared. So unfortunately, well, before I do that, first thing, since this plane is traveling at 5 miles and it's a constant height that's not going up and down, it's traveling at a constant height, the good news is that dh over dt is going to be 0, because if the height isn't changing, then the rate of height won't be changing either. So it'll be 0. And that's good news because that'll cancel out this portion because I have a 0 there. That's great. But I have an h, I got 5, I got dg over dt, that's negative 600, that's great, but I still need g. Okay, well, good news is I can say that the tangent of pi over 6 radians is equal to my height 5 over g. And so solving for g, I can say g equals 5 over the tangent of pi over 6. That's a tangent. And if you need to look up your unit circles, but the tangent of pi over 6 is square root of 3 over 3. And so this is going to reduce down to 5 square root of 3 once I've done that reduction. And if you don't see how to do that, ask me in class and we'll go over that. So solving for d theta over dt, I get d theta over dt. If I divide both sides by the secant squared of theta, I will have my d theta over dt, which is what I'm looking for. And then that will be negative h times dg over dt all over the secant, and let's do it right, all over the secant squared of theta times g squared. Okay, well, let's fill in the blanks. I know what a lot of this stuff is. I know that h is negative 5. I know that dg over dt is negative 600. I know that secant is 1 over cosine squared of pi over 6, and I know that g equals 5 square root of 3 squared. Okay, so the cosine of pi over 6, again, if you don't know your unit circle, you need to know that. And the cosine of pi over 6 is square root of 3 over 2. And when you square that, you will get, well, I know, well, let's just start over. Start on the top. Negative times a positive is a positive. 5 times 6 is 30 with 2 zeros left over. All right. 5 squared is 25 times 3 is 75. All right. And so 1 over the cosine of this is square root of 3 over 2, which would be squared. And so this thing, after I've done all my calculations, reduces down to 30. If you put it in, just again, just making it quick to get done here. And if you need me to go over how I simplified that, I can do it in class. But this is d theta over time. So since theta is, we've changed it to radians, time is in hours. We know that this is going to be 30 radians per hour. All right, well, that's a long one, and I know it is, folks, and I apologize for that, but this is some tough stuff, and it's very important stuff because they cover it very much in the AP Calculus exam. But the Star Wars fun fact of the day is about how they came up with the lightsaber sounds in Star Wars. If you go to this YouTube channel, you will actually find an old 1980s behind the scenes video of how he used a old projector sound and a microphone run behind an old TV set and combine them together to get the lightsaber sound. Well, like I said, this is a long one. Have a good day. Bye.